Hello. Today, let's talk about the components of the electrical circuits, or which is a basics knowledge about electronics, which you can, if you want to learn how to build a computer, how to build a television, how to build a mobile phone. These are all you have to learn these topics. Let's go to whiteboard. Okay, now there are many components, but if you just focus on the function of these components, and they can be divided into several, the number is finite, okay? And the first component is, of course, the source of the first is, oops, well, I have to change color. Well, can we just draw a circuit to start with? See, this is a symbol for battery. It's a positive sign, negative sign. And if you connect with, for example, this one, I'm sure you have learned that it's called the resistor, okay, whose value is called resistance. But today we're talking about additional components. That would be, yeah, that would be, I'll start from this symbol, something completely new, okay? And it's called L. And we'll just write down the name here. So R is called resistors, that electric resistor. Should I write the full name here? It's not a magnetic, it's electric.
This magnetic resistor?
Oh, we'll talk about that. Yeah, it's good to know the electrical resistance. Resistor. Okay. What is L? It's called electric well, because they have to driven by the current. Okay, it's called electric, but they have functions. Electrical inductor, yeah. Inductor come from induction, inductor. Okay. And the third one will be called, okay, this symbol, have you seen this symbol? It's called C. Yeah. And but bear in mind that in this case, I don't think you can this circuit work, okay? Because this is what calls oh, sorry, this switch. Just draw a switch here. This is just switch. Okay, that is switch. We just show that there are these three basic components apart from the battery and the switch. Okay, and it's called C. C called capacitor. So you call it electrical capacitor. Okay. Capacitor. Okay. The value of that will be we call resistance. Okay, resistance. So whose value is we call resistance.
Measured in ohms.
Yeah. Resistance. Actually, we just use R, and it's a unit. So that's a unit. That unit is called ohm. Okay. For the capacitors, for the inductors, that is whose value we called inductance. And we use L. I tell you what, it's called Henry. I'll talk about the Henry. Ohm, yeah, this is for ohms, it's ohm. Why we mention Henry? It's a non-story, okay? Be patient. H for Henry. Okay. Now how about the capacitors? Capacitor. So the value of the capacitor is an object, right? Whose value in the circuit is called capacity. Okay, capacity.
Also, how much
Well,
it can store.
we'll talk about you know how to define, how to study the capacity. So this is the name is. Can you guess the name of the capacity?
C.
F. What is F?
Faraday.
That's right.
Oh.
That's right. That's right. No. Sorry. The notation for the capacity is C. Just the first meter.
Yeah, the unit is
the
Faraday.
unit.
Yeah.
The unit is Faraday. Wow, you got a big
Henry
three.
Faraday.
And Faraday. F for Faraday. Faraday. And because the capacitors are relatively small, if you but that is so sometimes we'll use the micro Faraday. Okay. So this is just 1 microfarad will equal to 10 to power. Can you guess?
9.
No.
Oh,
micro.
6.
Yeah, -6 farad. See.
Okay. Nano.
So just so that's why sometimes. Oh, by the way, we put this is something we have to put there. I'll just focus on these 3. Okay, these 3 things. I'm going to talk about a unit of the charge. It will be also interesting because it got involved Coulomb. Do you want to talk about Coulomb?
Okay.
I got a charge here. Okay, I'll just charge here. There's electrical charge. Charge.
Charge is different from current. Right?
Well, charge is not a component of circuit. This is circuit. This is circuit. Okay.
Current is moving.
That's good. Let's put our title here today. So the components, basic components.
Oh, electric
components. In electronic circuit, because involved electron, the movement of electrons, so that called.
What's the difference between electronic and
electric could be just without much too complex, because we're talking about the circuit. Haven't finished that.
Yeah, okay.
Finish.
Circuit. IR.
So stop. Yeah. Circuit. Okay. Because we don't interrupt you while we're talking about something. Now, these are 3 basic components, right? The difference between electronic and electronic, because in the electronic circuit, that will involve more components than electric. Okay. Electric is such that we don't want to spend too much time. So electric is such that, for example, you have the globe, you got a globe, that's electric. Okay. So for electrician, for the electricians, that's it. That's electric. This is called electric. Okay. Circuit. That's difference. Okay. That's the difference between the electronic and electric. Because eventually, after we study these 3 components, we have to study more. This is basic. Okay.
Oh, no.
And electronic, so for example, that will involve the diode. Is another one. It's a diode. We mentioned diode, and it also can involve the transistor. You can do transistor. That's electronic. Okay. So that's why you got resistors here. You got the capacity here. So when you see this diagram, this is certainly different from electric. Okay. That's called electronic.
University.
There's difference between electric and electronic circuit. To back that, charge is not components, but it's invisible. Charge is so small. How small is that?
Electron.
So that's what electric charge. Okay, that electric charge is that we know the basic unit. So basically we know the electric unit. So the charge will equal to, the integers. This n is integers. Okay, time electrical charge of electron. Okay, charge of electron.
So that's of electrons.
So it's 1e. 1e. That's important. Some teacher don't tell you this, but you must learn that. This, if you want to know any basic numbers, this is very important
it's
one.
Important as pi?
Yes, it's important pi in this context. Yes.
Yeah, okay.
That's -19 coulombs. If you use coulombs, right? Now, of course, we don't confuse that because farad is also a unit for the charge. Okay, in the electrochemistry. Okay, I will not go that far. Okay. we got to connect fast. So that's the electrical charge. Now, but how about current? We just use current. So that is these are the quantities. So these are variables. There's time-dependent variable. So electrical current, that's called electrical current. In Ohm's law, we have learned that electrical current. So the notation for electric current is I. Here, because we want to differentiate from this notation here, do we use L or I?
L.
We use L?
No, we used I. We used I in the planning.
In this case. Yeah, probably we will use
L.
I will use L for time being, okay. In that case, I will comfortably use I or capital I, okay. Because that is, it looks a little bit weird if you use lowercase I. You just use capital I. If I have trouble, we have to adjust that. So what is I? By definition, I is a quantity of electrical charge passing through certain cross area per unit of time, the delta T. Or if you have learned calculus, that is the dq dt. Okay, remember the q can be the function of time. Not in this case, okay? In this case, if they have settled down, of course, in this case, there's no current going unless you have to use a second switch. Do you agree? You have another switch. Yeah, well, because you see, electron cannot jump from one plate to a plate. Oh,
they cannot.
There are many related questions. Before we go further, can we just focus on this basic relation? Okay, so that's how to write electrical current in terms of electrical charge. So this looks like, you know, the first derivative. Okay, so that is in general, we are dealing with this called transient. Transient state is actually unsettled. So, for example, once you switch off this this can we call it switch one? So this is S1 and S2. And once you switch S1, and the current will jump, okay? But it will take time, finite time, very short time, to build up, because in the meantime, they actually built up magnetic field. Okay? Yeah. It's solenoid. Now, I have to make some space here so that I will provide something important. So the unit is insignificant. We just use value, okay? Now we have also mentioned that the structure of the how actually related this symbol to the physical structures. For the resistors, the easiest shape or easiest shape of the resistor is cylinder. Okay, if you just draw this cylindrical, yeah, that's correct. Right? So this goes. So that's a physical dimension. Okay, what goes to it's a physical. How to say physical structure? Physical structure. So what is structure of the resistors? Resistors, just the simplest one is just uses cylindrical, okay? Cylindrical, that is how we just, you know, get it is cylinder, a small cylinder, right? So that, do you remember? We have two parameters here. We had A for a cross area, and the length. Okay, there's two geometrical parameters, okay? So this is called the cylinder, because the cylinder, that could be cylindrical. How to say? Cylindrical, yeah. Cylindrical resistors, because it talk of the cylindrical shape, okay? Of course, there are other types, the cylindrical resistors, okay? Of course, they can build a different shape. For example, they can use the cross section could be square or rectangle. Okay, but of course, the circle is the most convenient. That's why to calculate the resistance R here. So this is the formula you can use. R will equal to a constant called, is that determined by structure? No, that's a rho. It's Greek letter. it could, because the resistance logically that were it will be proportional to the length, okay,
yeah.
and inversely proportional to the area. Because what does resistance do is that if you enlarge this side, so basically what happens is it's a kind of it's not good conductor, but it is conductor that with a little bit resistance. So this resistance could be the positive lattice, okay, the structure. So that is a positive. So the electron is that once you switch off, for example, the electron will move. Okay, in this case, where electron, of course, if in this case, electron will move to the positive direction. Okay, because why? Because this is the potential is higher. So this is a V plus. So this is a potential. Okay, this is a potential V plus. This is a potential V0. Normally, not zero, but negative, should I say? This V negative. So normally we call the negative the earth. Can you see that? This you are going to see some diagram. When we say this symbol, we just assume that no, not just negative, but also equal to 0. Okay. So which is when you earth somewhere, which would be the lowest potential in the circuit. Okay. Of course, this would be higher. For example, this could be the voltage could be say 9 volt. So this would be 0. There will be 9 volt. Bear in mind, so these are all perfect, ideal conductor. So they have no resistance. So in this part, resistivity is equal to 0. Okay, this one.
The wire is a superconductor.
It's superconductor. So they are all ideal. So these are all called ideal components, ideal electrode components. Okay, ideal components. So that is very important. Ideal is model. Okay. For example, first we are talking about wires. Okay, this wire. First is wire, or conductor wire. Okay. So this is when you see that you contact with 9 here. Okay. In this case, the R is the resistivity of wire equal to 0. Okay. And then we're just talking about then everything is ideal. Okay, everything is ideal, and so that's something I have to mention that we're not dealing with real. Okay, so in other words, wire in RLC is considered as a not just conductor but a superconductor. Okay, because only for superconductor can we say the resistivity is 0. Okay, of course that's just for convenience. In practice, it simply means that if you use a copper or even use the silver, even use the gold, right? Then which means relatively speaking, the resistivity is approximately to 0. Okay. In actual calculation, you don't have to determine. You don't have to pay attention to the resistivity of the conductor wire. Okay. You only pay attention to the components, which is focused on this in this structure. And how about inductor? Inductor is just a solenoid. So if you have a solenoid, just if I just draw this cylinder shape, right? You can use a coil. You can use the how to say coil. So you can make cylinder oil. So this, if you just draw this one, so that's how to build inductors. Okay, inductor is just a solenoid. It's also the same cylindrical solenoid. That's called the solenoid. So that is the L. So this case called the cylindrical. Okay, that's also it's just solenoid. People know about the solenoid. Solenoid.
Is it AR?
Right. Solenoid. ID. Okay. It's called a solenoid.
I thought it's ALAR.
Solenoid. Okay. Solenoid inductors. Okay. Inductor. Okay. You just this is something new for you. Just pay attention to this new name. Okay. And for the capacitor, what is the physical structure of capacitor? The way of we have to, if you in 2D form, it's easy. Now here I draw the 3D. Okay, it's just two parallel plate. Okay, okay, parallel plate. Conductor, they are conductors. We use this model. We use these devices to study electrical force all the time. Okay, so these are the conductors. Conductor plate. Okay. Parallel, because they are put into parallel, they're called parallel. That's right. Let me finish before you ask. Okay? Parallel. That is how, that will give you the physical structures of these three components. Okay. Now, what are the role of each of these basic components? We know that for the resistors, okay, can we just do it to study one by one? For the resistors, what happens once you have applied, once there's a current goes through the resistors. So what would happen? So many conditions will occur, right? For example, if you just consider the electron, because in conduct it's an electron which is free, okay? Or they can move. Obviously, if in the solution in the vacuum, okay, once you apply the voltage, if you have applied the voltage here, I just draw a proper diagram here to draw your attention to the potential difference. So there's this electron here, right? If you create a voltage, for example, this is a positive and negative, right? So that in that way, so these if you connect them together, as I said, well, the negative is earth, okay, which means all part of this one is zero. You agree? So this would be in this case the potential here in all this. So that has the positive potential, right? So that's positive potential, and this one would be negative. Okay, negative. So of course, according to this donation and notation, that and also that this one is also, can you see, it's everywhere, because this is a wire without any resistance, electrical resistance. So to be exact, like equal to zero. So when you see this sign, we just set this potential value equal to zero, because it's easier to remember. The voltage of this one, so the voltage, or so sometimes they call the voltage, okay, is actually the voltage actually represents the difference, potential difference. And so that's called the EMS, so the EMF, so EMF, so you call the electrical motive force. Of course, this is just a fancy name, okay?
Oh, this is fancy.
No, it just says charge will be moved.
Oh, so it's
in the battery, okay? Oh. Battery can move. So battery,
because there's a potential difference.
Because of potential difference. So you don't have to mention this force, but if you know that, if you use the potential difference, that would be potential difference with positive potential minus negative one. Okay. Of course, if you just say it's just equal to V.
Positive.
Yeah. If this just equal to V. Okay.
It minus zero.
Okay. Now, by creating this potential between this side and this side, the electron will move, because the electron can feel that the potential is higher on this side. This is, can we draw that diagram? Because last time I was explaining this phenomena. So what can we do is we can use different colors. So for example, if you want to draw the potential, not the current, you want the potential. So basically the potential will change. So the potential will change from here. This will be zero, can you see? How to draw that diagram? On this side is lowest, okay? This is lowest. Once you cross the battery, they will increase. Can you see? They will increase. So that potential difference secreted by chemicals originally stored in the form of chemical energy. So, but during this, then when they travel across this conductor, it's constant. In other words, in this anywhere, the potential is same. But if, of course, it's only one, we just assume there's only one resistor here, the potential will drop, okay, when they cross that resistors, and then return to the lowest one, which would be 0, you agree? So that is how you draw this diagram, where, so that is a diagram of potential. This is a potential. So potential, if you draw, yeah, that would be the potential. This would be 0, okay? That would be the potential. So the potential will drop. See, from here, the potential will drop.
To 0?
To 0, yeah. Oh. Because it's the same, can you see?
Yeah.
This is a bit of a conductor. Now, according to Ohm's law, so Ohm says, that's why the first thing, that's why Ohm is introduced. Ohm says that if you measure the voltage difference between these two, so can we call this is this also, can we call it V2, okay? V2, V1, okay? Ohm says the current can be divided across this resistor, can be written as delta V, potential difference.
Delta R.
And divided by resistors, that's resistance R. So what happens is that when electrons move, they are not free. So the motion is not free. So basically, when electron move, there will be, unless, of course, the R is equal to 0. Okay, you can see that R will be 0. Otherwise, the current will increase enormously. So if the electron can move freely, then which means R equal to 0. Okay, so therefore the current will be infinity.
Oh.
Do you agree? Yeah. That's true. True. So normally we just simply write this as V over R. Okay, but bear in mind this V is the potential drops across the resistor. Okay. So that is famous Ohm's law. Yes, indeed. If you draw the diagram for that one, for this is what I talk about in this page. On this page, we just talk about resistor. Yes, indeed. So if you draw the current as a function, so if you treat I is a function which is depend on the potential difference, right? So basically, as the increase because it's linear, right? It's linear, it's proportional. So if R is very small, so the gradient will be large. You see, okay. If R is large, then the gradient will be small.
Yeah.
So that is how we actually build. We can build that. We can use different material or compounds
to build
a resistor in order to obtain required current. Okay. So this is a this is a small. So R is very small. R is small. R is small, right? And this so R is large. Okay, R is large. Now this device is useful. For example, in the practice, for example, if we just say if we want to have the globe right here, we just want the globe to illumination purpose. Then we will choose the resistance for this globe, so that the power, power can be written as a product of current and voltage across it. Okay. Now, because this power is dependent on the product of these two, then we can, using Ohm's law, we can rewrite, for example, current. If we substitute the current into that, we get the V squared divided by R. This is something very useful, okay? Although it's simple, right? Alternatively, the current, if the current is constant, then we can rewrite in the form. So this Ohm's law will also give you V equal to R times R, right?
Yeah,
I
yeah.
times R.
So it's I
So
squared.
I R times I squared.
Yeah.
Okay. In either case, is that of course there's no guarantee that the current will be because current, in our opinion, is determined by the voltage, the ratio of these two. Okay, so when we just decide, say this is the power of the electric globe, we can actually we use that to every day. Now, if we want to this is more powerful. For example, if you want to if they just draw another diagram here. So if you want to, if you use the word brightness, if you're looking for the brightness, okay, and for example, if you want to use a very bright globe, so if you want a very bright globe, so we are expected that for the fixed voltage, we can use this form, right? So basically, if V is fixed, so V is constant, V is constant. In this case, so can you draw the diagram? Do you know how to draw the diagram here? The dependence of the power of R. P and R.
Oh, inversely.
Yeah, inversely, like this one. So that is very practically important because the electricians can choose, or actually the manufacturers rather.
The graph that
they can by just reduce the R, they can increase the power or brightness. You see, so that is difference between different globes with different power. Okay, because they said also is the watt. Do you know watt?
Yeah.
What is watt? Yeah. So what is so power by definition? Power by definition is equal to the work done.
Oh yeah, over
time interval. Interval.
It's joules per second.
That's right. Yes, because they are all famous. That we mentioned this. So the unit is watt. So they are famous people here everywhere. Watt everywhere in this study room. Watt for W. Okay, and joule for J. So this is the unit. So this is a unit for the energy, for the heat. Do you know heat? So confused. We use the capital Q here. Sorry. Yes, heat. That is not just the heat. It's heat. As well as work. Okay. Any energy, the kinetic energy, the potential energy. Okay, the potential energy. Okay.
Elastic
and the binding energy in nuclear, also known as capital B. The binding energy in nuclear physics, do you remember? The binding nuclear, yeah, the binding energy average. And in chemistry, you have the activation energy. So all these in Joule, okay? In Joule. So in history, I will not go too far. In history, you have the calorie. So forget about calorie. Calorie is nonsense. Calorie is a bad idea. Okay, it's not a scientific idea. It's just old sagas.
That nutritionists use.
Always nutritionists for draw people's attention because nobody uses that, so they think they are they are doing something very, how to say, very abstract, so that
very
people
scientific.
Just not necessary to that's fancy name for people. Okay, that is resistors. Okay, so physically, what we can do, we just record that. How do we determine resistor? Resistor were just resistance in the formula of resistors. I write down here. So resistor for formula here is R were equal to a constant rho, and which is proportional to the length. That will be the length of the conductor. That will be the length of conductor, and its cross area. So it's cross area. So that's how we wrote that. Alternatively, some people write that as sigma, 1 over sigma. So the rest formula are the same. So in this case, the law is called resistivity. It's property of the material. That's called resistivity. And how about sigma? Can you guess? It's it's reverse. It's a receptacle. Can you give a name? Permissivity, well, it's just simple conductivity.
Oh, okay.
Conductivity, because you say that is just reciprocal. So you can draw similar graph here.
Yeah.
If you draw this diagram here, draw the diagram here, draw small. So these are all reciprocal, they're inversely proportional to each other. So that, do you know that? Probably sometime we, so this is a, for example, is a rho. There's a rho. This is called a sigma. Okay, sigma is conductivity. Same thing. So the dependence of these two variables is simple. You see, it's just it's different color.
Oh yeah, it's inversely proportional.
Inversely proportional. Can you see? You can see. You understand? So, in other words, a good conductor. So, for example, a good conductor.
High conductivity and low resistivity.
That's right. That's right. That's how the physicists doing this trick. You have to be. It's simple. Okay, just logic. That would be safe. A good conductor, very good conductor, and then that would be very smooth conductivity. How about a superconductor?
Zero resistance.
Yes.
And infinity conductivity.
The conductor would be infinity. So that's why. So that would be. Conductor can be approached to infinity. Okay.
Yay.
So that is how we denoted this is formula of how to remember that is a formula for calculating the resistance. Okay. So next we'll move to the. Perhaps today we'll just focus on the capacitor first. Okay. I didn't realize that there are many related topics. What I'm going to do, I choose this color. And it's important, I just draw this box here. And this also equally important, okay? It's almost no, and that is a power formula, right? Okay. Okay, that's all for the resistor, and whose value is called resistance, whose formula, if it's a cylinder, we can purely based on the one parameter, the constant called resistivity, and the geometry parameter to determine the value of the resistivity. So physically, we can determine the value, but their role of resistors is actually to alter, to change the current for the giving, you will get different current
that we want. Like
we want.
Desired
In other words, the resistor is play a role to control the rate of the change in the current flow. No, in charge flow.
Why can we also change the voltage?
Well, if you change the voltage, ultimately you are dealing with the movement of charge. All right, because this is a charge. It is a charge. How do they do work? So, basically, this is called the dissipative. It's called this component is called. Okay, it's not conservative. It's other way around. I just choose it. So this in general. So in general, a resistor is called a dissipative. To write with dissipative components. Okay, dissipative which means that consume energy. Always consume. Consume.
So it can it can be used to control the current output.
So this dissipative device is the current. So the R is dissipative. It's called consume energy, or it's just always one way. Not destructive. It's just lost energy. So energy. So that means energy will decrease. Always wasted or consumed. Not decrease. Consumed. How to say? Consume. Energy consumed. Okay. So this R is different. We're compared R with C and L. Okay, let's go to next page. So then we're talking about the capacitors. Okay, we jump to the capacitor first. Capacitor. So physically, the capacitor here I just draw the two-dimensional. Okay, if I just want to draw I can draw a three-dimensional. That is a capacitor. So I just do two-dimensional, three-dimensional rather. There's one plate. This is one plate. Okay, this is one plate. Of course, they have some thickness. We're neglected that to have thickness. That is a two capacitor in a 3D form. So that will be, I'll just write down here. Okay, that's two capacitors. Metal. So the metal plate. So there's two. So basically, we're dealing two. Two parallel conductor plate. Okay, plate. The important feature of these devices, of course, if you just the 3D form, so that's 3D form, so we connect with wire. But it's convenient for us just do the 2D. So this 2D diagram, we can just do two parallel lines. In this case, we just make the thickness. So you'll be able to see thickness. You used to see the thickness of that too. That's called the capacitor. I think it's different. See, unlike the resistors, there's no connection. There's no conductor between the two terminal. Between the two terminal. That's just two plates. It's air. It's no point to make vacuum. The resistor. Oh, by the way, the conductivity of air and the vacuum is almost the same. So very near insulator. It can be treated as insulator. So what we do in the real world is that we just have used different. Yeah. So basically, in this case, we can connect them with support certain batteries. So if you just consider, if you just just to say, for example, this is positive, right? This is positive. Longer one is positive. This small one is negative. So if you do that one, we just make a switch here, just realize and put draw attention. If I also put ammeter here, it's called ammeter to measure current. Okay. Now imagine what would happen if you switch it on. If you switch it on, if you connect it. Okay. Once you switch it on, because this originally this is neutral. Okay. So the electron, so the electron will go this way. Okay. Once you switch on. And of course, that's what you call the current goes that way. So that's right. The current, that's this direction of the positive charge move. So that will be current. There's current. So the current will go this way. So the current will go this way. So this current will go. Current one way can be described in the positive charge move. Can you see? So you can just imagine that's equivalent. So eventually you will see that the current will go there. Eventually you will end up this charge will move. So the charge will move, okay, to this side, okay, or both sides, okay, both sides, just to two sides. So that's full of charge. The full of charge here. And of course, as a result, the electrostatic field will be generated. This is a negative. Okay, this is a negative. This of course just go to. You don't have to draw all. Just draw some of it. Then there's as a result, electrical field will be generated. Okay, from zero, from vacuum. So we use if this color, so there's electrical field will generate the position. The direction will be from positive to negative. Okay, so that would be it's uniform. Okay? It's uniform between the two plates. Actually, if the gap is very small, and it will contain the most of the electrical field. Okay.
So if it's smaller and larger,
if the gap is small, so the distance between the gap, we use D, and normally we use D for the distance between the two gaps. So this physical distance called D, that is between the two gaps. Okay, and also they got area. Okay, so this area, A for area. So A is distance. A is the gap distance, gap, and gap distance. And A is the area. Okay, physically area. Now, what is this device can we do? So in the first place, we know that the charge will form. So this is a negative. This is a positive charge. Okay, this is a negative charge. Okay, once you switch on, and after you switch on, and it will stay there. no move. Okay, so eventually the current will settle down.
Oh.
You didn't know that? So if you're really interested into this device, that we have to mention this process, detailed process. When you switch on, and the current will be increase and then decrease. Okay, so if you draw this, how to do this diagram here. So this is time dependent diagram. This is time dependent diagram. Okay, this is T. This is T. And can we say this is current or charge?
Charge. Oh, current.
The current is the current. So the current is a function of time. So very quickly at 0, we switch off. Okay. So current will increase and decrease. You agree? You settle down. Yes. So basically, it will decrease and increase. So basically, it's very shortly. They just we just exaggerate that. That's very. Oops, sorry. It's current. Here's the color. Here's the color. So current is the red one. So current will. I'll just use a very small time unit. So it will go up and decrease. Okay.
Yeah.
Now. So how many charge has been going through? Can we just calculate how many charge here? That area. So what is difference? What is the relation between the charge? Yeah.
Charge, current, and distance.
No. So because by definition, I equal to dq. Can we use small q now?
Okay.
Because I realized capital Q is reserved for
eternal
heat, not for the heat. So it's no case.
dq over dt.
So therefore,
q equal to.
No. dq. Just do some calculus.
I know. dq equal to I dt.
Yeah. But bear in mind, I is a variable. Okay, variable here. So
integrate on both sides.
So you integrate on both sides from time to time. Say this is time. Say to infinity. You can integrate to infinity.
Okay.
Time infinity. That would be dq. And that would be they say the I, dt. Which is function of time, this is function of time, dt. And dt from 0 to infinity.
So q equal to blah,
so that would be the delta q. Okay, there will be delta q that will be equal to delta q, or equal to that area.
Yes.
See? Yeah. Sorry, we use area again, but how do I use this area? How do we devote this area? We do not use A.
Oh, we don't have A anymore. We just like delta Q. Just like delta Q.
Yeah, can call it area. Okay, I still call area. Okay, this is not acceleration. Okay. So it's just equal to the area.
Alpha.
Okay. It's alpha. Can we call it alpha? Alpha. A for alpha. Okay. So because initially, so that is the Q. That I still use capital Q. Yeah, I use capital Q. Sometimes we have to.
That's okay. We're not doing thermophysics, so it's.
We're doing thermophysics. That equal to Q minus 1 equal to this alpha. Okay, that is area. Okay, so alpha is the area. Because in IB sometimes we use this diagram, the area under IT graph or IT curve. Okay. Okay, it is area. So therefore, we got this Q. We can store the Q. Okay, Q equal to that area. Okay. Now, of course, this is not convenient if you always use this area. Okay. So we're interested because what we do is that eventually, ultimately, what is the potential difference across this gap?
Potential difference.
Yes, if this voltage is V. If this voltage is V, what is the potential difference across these two? What is the potential difference?
Oh, it's V at this position minus V at this position.
So delta V across the plate will simply equal to, we can use a higher one. And this one, this is a V plus, this is a V minus.
V plus minus V.
So V plus higher minus V minus zero is just equal to V, the voltage. Okay, the voltage. So therefore, we just can say, in this case, obviously, and we can argue that the charge stored will be proportional to the voltage applied. Do you agree?
Yeah.
The higher the voltage, the more electron will be stored.
Yeah.
So then in that case, we can introduce capacitor that Q will equal to CV.
What? So C
Okay,
is like
C is capacitor.
capacitor.
Okay, so therefore we got this formula. So therefore
scalar.
no,
Scalar
this is scalar.
number.
Yeah, that is a scalar number. They're equal to V over Q. Can you see?
Yeah.
Do you agree?
Yeah.
That's its definition of capacitor. Capacity. So C here is introducing. So that is C is where C is called. Okay, is denote. So C is called electrical capacitor. Okay, capacity.
It's voltage over charge.
So you see, obviously that this C will be determined. Just put the formula here.
Mm.
So this C obviously will determined by the physical dimension of this one. Okay. In particular, we can use the common sense. The narrow the gap,
and the greater the area,
the great the capacity. Okay.
Yeah.
The greater. So that would be the formula for the capacitors, right?
Yeah. Yeah.
Okay. Now, because of some reasons, they have to put the constant here. That's called epsilon E here.
Okay. What is?
So that is the property. This property of medium.
Permissivity.
Permissivity is what is epsilon. Epsilon 0. That's epsilon. Or say epsilon 0. This is for the permittivity in the vacuum. Vacuum. Last time I read it wrong. So this one vacuum is 2U, right? Vacuum. Do you agree? This for the media. So this is a media. Could be air, could be a substance. It called media. This called this they have proper name here. It's called the dielectric constant. Dielectric constant. Okay. Vacuum. Okay. It's called. So this is permittivity. How to say? Permittivity, right? Permittivity of vacuum. Okay. This is permittivity. Permittivity too small of dielectric. Okay. Electric material. Electric medium. This is a medium.
Fancy.
Medium. It's just material. It could be some plastic. Okay.
Air.
It could be crystalline. Please just keep. So that is the formula. So that anything important, I will put the color. Okay, just keep. We continue. Okay, we'll continue. That's going to be this important formula here. We got the formula for the resistance. Now we got the formula for the capacitors, because that is a simple formula here. So that is how we obtain that. Now the question is, what is the role of capacitor in the circuit? Of course, we say they can store the charge. Yes, the storage. But more importantly, they store the electrical energy.
Oh.
So we are interested to find out how much energy can a capacitor store. Okay, this needs to be too crowded here. Can we still use this diagram? I use next page. So the role. So basically, a capacitor. So we just write down here. What is the role? A capacitor. Oh, sorry. The role of using a capacitor is to store electrical energy in the form
Of electric.
in the true form of what? Of
field.
Electrical field. Okay, so that is the key. Now, the immediate question is, how much energy can be stored for the given capacitor? So given C and V, okay, because the voltage can be adjusted, given C and V. So how much energy can be stored, okay? Now this is what, because if for electricity, we just use the energy, can we use U, okay? That we will use U for energy. That's one reason. So the electrical energy, U can be calculated. Can use calculus. You want to use calculus again?
Okay.
Because you are going to have calculus test. Yeah.
What?
Calculated, right? How? Let's do it. So let's just assume that we just draw this one. So with this one, I just draw the parallel. We just probably it's easier to draw this one. We see just like mountains. We just do some analogy with the gravity. Okay. So basically, the how much energy will be stored will depend on how much work is done. Okay. So that's where we can use the basic law in physics or in mechanics, Newton's mechanics. So for example, this is just same setup, just I put rotated by 90 degrees. Okay, give you just a feeling that you take some effort to move the charge over there. Okay, so for example, this is positive. If you want to move the positive charge, okay, across this one, so that you have done the work. Do you agree? So basically, if you want to remove this charge to here, remember this distance is d, okay? This distance is, the gap distance is d. Now how much work have to be done? So this is v. So first of all, can you recall that the formula?
Force by displacement.
Yes, that's right. Can you recall the relation between the electrical field and the voltage or the potential difference?
Electric field.
Yeah. So this electrical field strength, okay? Electrical field is downward, of course, it's vector. In general, it's a vector, but we are only interested in the magnitude. Okay. So what is the definition? Do you remember?
It's proportional to.
No. It is by definition. So electric field equal to the gradients.
Yeah.
Gradients. Delta, can we call the delta V, delta X?
Okay.
So this we just use to do that. Can we just use x-axis here? So it's important when you solve the problem in physics, you draw the proper diagram. This is your axis. So can we call it 0? In that case, that the other end will be d. Okay. Yeah. So we just move this charge. Okay. So we move the charge. Can I just draw the animation? I know this how to do the animation. So, yeah. So basically, what you do is that we're going to calculate work done by move this object up, obviously by external force. Okay, yeah. So obviously the work, the force must be opposite.
Negative E times D.
Yeah, no, it must be negative, right?
Yeah, negative.
Be negative. Otherwise, you can't move it. Yeah. You cannot move here. So what do I do is that oops. Okay, so that is E. But in a simpler case, in a simpler form, because when you solve the problem, you must be quick. Okay, that will give you the formula that the V will just the potential difference of this of the battery, and divide by the gap distance. That be the that's E. Okay, first formula, and then how about the force? Electrical force will equal to Q. We put the Q here, Q times E, right? Q times E here. And you have to move everything across this gap, okay? So that is electrical force. Electrical force downward. Okay? So the work done, will be calculated because it's variable. You see, you can't, but you can just consider as in a how to say? Can we just integrate this work by just consider a tiny amount of charge? Tiny amount of charge. Can you see dq. So the force, how do we divide? Can we just each time we just, this is force. Each time we just have a little amount. How do we calculate that one?
dt.
Yeah. How to calculate the work done?
Force by displacement.
Because we can either pick up a little bit of charge, we can use it, we can denote as a dq. Oh yes, that's right. We can use that. That's where equal to d. That's by definition. We can't escape that.
Dx,
We can have
okay.
that is a for. Then that will be from 0. Can we from 0? Let's calculate
To d.
to d. Okay, to d. Now the force. Yeah, we can rewrite the force. The force will equal to into this q. Okay. Q, of course, we don't deal with large quantities of Q, so we introduce the dq. Can we see? So in other words, in our case, the F will equal to the electric field acting as a small amount of the Q. Okay, dq. So that's the general form, the special form. So
what do you mean dq? So that's just
dq.
one charge.
We just need to pick up a little bit charge.
Okay.
One time.
One at a time.
One at a
Like
time. Yeah,
infinitesimal.
you find decimal. Otherwise, we can't, because G is changed. Do you notice that it's time dependent?
Yeah.
So what we do, we substitute this F into this formula. We got dV. That is dV. Okay, that's dV. Okay. Can we just use it, rewrite it into this calculus form? That would be dV dx. Okay. Times the dq. Can you see? Do you agree? And in addition, what else? We have dx here. Do we have dx here? Oh, not dx. This is dx. Sorry, you have dx here already, not dt. Be careful. So just a reminder here. So basically, what we from here we can obtain that the force. Okay, the force can be rewritten as dv dt. Okay. Sorry, not dt. That's dx. Gradients in space. Gradient in space. Time dq. Okay. That makes sense now. So if you, so this is question 1. I will just stop here. We just call this. If we call this, yeah, let's call this equation 1. This equation 2. So we're going to do it very quick, slowly. So we substitute. We can sub equation 2 into equation 1. That's how to solve the problem. So equation 1, we obtained that the W work done were equal to integrate the dV and dV dx. You see,
dq.
And dq. Okay, time dq.
Can you cancel out the d?
Dx. Yeah, we have the and the time dx. So they cancel dx. Okay, what do we have?
dv dq.
You got a dv. You got 2d here. Something wrong? dv dq? No.
Is one of them a constant?
I
think q is a constant.
Q is not constant.
V
either what's going on here?
V? Would V be a? Isn't dv
Oh,
just V?
I see. We can't do this shift by, it is dq, or do we have to use dq here? Because what we go to next is simpler. So basically we have to replace this by the C. C equal to what? C equal to V over Q, right? No, this is very wrong. This is wrong.
No.
Can we just go back? C is equal to Q. Oh, how? I'm wrong here. No, this is wrong, okay? So the correct notation is that V I think the V were proportional. This is how they introduced this V were proportional to Q, right? And then therefore they introduced the C in this way, CQ. Okay, so the capacitor, so this is terribly wrong. So basically the formula correct for C were equal to V over
C. Oh, over Q. Yeah, it's the same thing.
Huh? Same thing?
Yeah. V over Q. Look.
Ah, CV. No, it's other way around.
V is proportional to C.
Hey. Something wrong is here. You see, even if I don't use that for a while, I'll get trouble. Let me see. How do they define the capacitors? Just go back. You need to find textbook, this one. How do they define capacitor? Perhaps take a break. Okay, I'll take a break. We'll work out this formula. We'll continue this discussion.
In part 2.
In part 2, we'll stop that for a while. Yeah.